A wave is any traveling disturbance. It carries energy from one place to another. There are two types of wave. The first is a mechanical wave, which requires a medium to travel through. In other words, the particles need to be physically connected. And there's a non-mechanical wave where energy can be transferred from one place to another without a medium. And the only way that can occur is with light or electromagnetic radiation. And there are two types of mechanical waves you need to be familiar with. The first is a transverse wave, where the particles are going to vibrate perpendicular. That symbol doesn't print out very well, but that's perpendicular to the wave's velocity. In other words, an ocean wave is a good example of a transverse wave. The properties that you need to be familiar with are amplitude, which is from the rest position to the maximum height. So that's a distance measurement in meters. So we talk about that being from rest to crest. So crests are at the top. Or you could go from rest down to the bottom, which is called a trough. Wavelengths are also a distance measurement given by the letter lambda. So lambda measured in meters. And you'll see that that's any distance between repeating parts of the wave. If we go from start, which is right over here, if I go through one complete wave cycle, I'll go all the way through a crest, through a trough, and back to the original resting position. So that would be the distance of one wavelength. I could also measure it from crest to crest. So if I pick two spots there and I went directly across, or of course trough from trough. Any two spots on the wave cycle that are repeating are called wavelengths, the distances in meters. Longitudinal waves are waves that travel where the particles vibrate parallel to the wave's velocity. So parallel to the wave's velocity. This example here is a slinky that's getting pushed on, so the push from this end will compress areas of the spring here, and then immediately behind that and in front of that area will be an area called rarefaction. Compression is usually associated with high pressure, and rarefaction is associated with low pressure. A wave pulse is a single disturbance, a non-repeating action that travels through a medium. So if I slam my hand on the table, I will create a pulse, a sound wave that travels through the air molecules of the room. A traveling wave is any wave that forms a regular repeating vibration. So ocean waves usually come into the shore as a traveling wave because there's multiple waves one after the other. When we measure waves, the measurements that we use to describe wave motion, so period, which is capital T, measured in seconds, frequency, little f, which is measured in hertz, and on your formula sheet, remember how those are inversely related, so the period is equal to 1 over the frequency, or we say it's the number of seconds between cycles of the waves. Frequency, on the other hand, is the measure of 1 over the period, or it's the number of waves, or events per second, and it's measured in hertz. So hertz for frequency, seconds for period. Wavelength we talked about as being the distance between two successive points, and amplitude is the height of the wave measured from the rest to the crest or rest to the trough. Measuring the speed of a wave, we can use the regular equation as we've seen before. Speed is equal to distance divided by time, except for in waves we talk about the wavelength being the distance and the time is measured as the period. And because of the inverse relationship of period and frequency, we can often see it written as lambda times the frequency, as stated in the equation that we see. The other formula that you'll see is a wave speed relative ratio equation. Speed of the wave in the first medium over the speed of the wave in the second medium is equal to the wavelength in the first medium divided by the wavelength in the second medium. Quite often what happens is a wave will travel from one type of material to another, and it will change speed and therefore change its wavelength. So some worked examples. Example number 1, a water wave has a wavelength of 5.7 meters and a period of 1.8 seconds. What is the wave speed and frequency? If we know that our period is 1.8 seconds, let's do the inverse of that number to find out the frequency. So frequency is 1 over the period. In other words, it's 1 over 1.8 seconds. And you can see on your calculator that comes out to 0.55 repeater hertz. If I want to know the wave speed, it's simply the wavelength times the frequency. So the wavelength being 5.7 meters, and I multiply that by 0.55 repeater hertz. And that ends up being 3.2 meters. A microwave oven emits microwaves at 2.7 gigahertz. So frequency 2.7 times 10 to the 9 hertz. Make sure that you change your prefixes into the base unit. And chocolate chips are all over the bottom of the plate, so we want to see at what distance will chocolate chips melt from each other. In other words, what is the wavelength of this microwave? On your formula sheet, you can see that microwaves are a form of electromagnetic radiation, which is given the letter C for speed. So the speed of light is 3.0 times 10 to the 8 meters per second. It's under the constants on the formula sheet. So looking at your wave speed equation, speed is equal to the wavelength times the frequency. We have our speed, which is 3 times 10 to the 8 meters per second. Our wavelength is what we're trying to find, and our frequency is 2.7 times 10 to the 9 hertz. Solving for wavelength, you'll see that it is 0.11 meters. So 11 centimeters. From other chocolate chips, you'll see them starting to melt. Last one, deep water waves traveling at 4.3 meters per second with a wavelength of 16 meters enter shallow water and slow down to 2.7 meters per second. What is their new wavelength? So this is our wave speed equation. The velocity in the first medium over the velocity in the second is equal to the wavelength in the first over the wavelength in the second. So stay consistent with the different substances that you're staying in. So we'll start off with 4.3 meters per second in the deep water. So that's the 16 meters on the wavelength for the medium 1. And in medium 2, we're going the slower medium, 2.7 meters per second. And we want to find out what the wavelength is in that medium. So we cross multiply, and we're left with 4.3 times the wavelength in the second medium equals 2.7 times our 16 on the other side. Divide both sides by 4.3, and you'll see that our wavelength in our second medium is 10 meters.